All right, here we are again. So I see everybody's here. Very nice. All right, so here's what we're doing today. So we're going to do the rest of chapter 6. It'll just about exactly take up the entire time. And when we're done with that, there is a problem set on Moodle. Let's go take a look at it. Here we go, Moodle. Let's log in. Yes, so if you look down here, yes, there's a problem set for chapter 6. And because we'll be done with chapter 6 today, what I'd like you to do is download this and work on it between now and Thursday. It's not maybe quite as long as some of the other ones we've done, but it's pretty involved. And it's excellent practice for what we've been doing. So why don't we do that? And then we'll carry on with the new material. At some point, though, we do have to start thinking in terms of a midterm because chapter 5 and 6 represent the first midterm. Now, before we do that, we'll have what's called a sample midterm that we can practice with together. And then at that point, I can send you the actual midterm, which, you'd have plenty of time to work on it. There's no rush, but, we just want to make sure that we're ready to have this thing. And probably by now, you're starting to have midterms in your other classes anyway. In fact, this is probably the latest one that you're going to have. Not that long. In other words, it was designed. Remember, these tests were designed for the in-class setting when we had an hour and 40 minutes. So if you sat down and did it from start to finish, it was designed not to take more than, let's say, an hour and a half to finish it. If you work on it in bits and pieces, of course, it might be different. But it was intended to be handed out to you in person in a physical classroom setting when you only have that one period to finish it. So it can't be that long. Okay, and there's less, let's face it, it's only 2 chapters. It can't be, there's only so much material we can do. Oh, no, it won't be like, no, those practice problems were designed just to get us as much practice as we can get. It would never be that long. No, not even close. Because, there'll just be a bunch of representative problems that I've picked at random from what we've done. It won't be nearly as long as those guys. They were quite long. I agree, but no, this will be much more toned down. All right. Anyway, yeah. So don't worry about it. It'll be fine. All right. You'll have plenty of time to work on it, and it won't be nearly as long as the problem sets were, especially that third one. Oh my God, that took forever. All right. Anyway, so let's get. Yes, go ahead, Noah.
Why does it say on the grading thing that there's 2 midterms? Are there 2 midterms?
There are 2 midterms. The reason why
I have the same format, both of them.
Yes, everything is exactly the same.
The winner of the dates for the second one.
Oh,
first one.
End of March, maybe early April.
Because they're not super close together. Okay.
No.
Are they both on chapters 5 and 6 or on different chapters?
The second midterm is on different chapters than.
Okay.
There's 2 midterms. Okay, go ahead. There's 2 midterms only because if we have one midterm, there's so much weight placed on the midterm and the final. It makes people nervous. I think it's just easier to have 2 midterms and 1 final instead of having just one of each, because that way there's more material on each test and it takes longer to get ready for it, and there's more risk if you do poorly on it. All right, anyway. Okay, so all right, let's get going. So where we left off with was the inequalities. That's right. We just started to look at the idea of inequalities. So we know how to solve linear inequalities. We basically algebraically rearrange the equation to solve for x. I mean, that's really the bottom line. But when it comes to inequalities, the algebraic rules are slightly different. Okay, you'll see what I mean in a few minutes. You've run into this before, most likely, but you may have forgotten about this. So first things first, inequalities can take one of the following forms. The first one is strictly less than. The second one is less than or equal to. The third one means strictly greater than. And the fourth one means greater than or equal to. All right. So what that implies then is that if x is strictly less than 0, we say that x is negative. Oh, yeah, go ahead.
Yeah, I don't know if you got my message in the chat, but I'd like to speak to you after class about something.
I see it. Yes. Okay, we'll do that. Just hang on when everyone else is done. All right. Anyway, if x is less than or equal to 0, we say that x is non-positive. That sounds strange, but non-positive because it's either negative or 0. We collectively call all those numbers non-positive. When x is strictly greater than 0, we say that x is, of course, positive, but if x could be 0 or positive, we say that it is non-negative. So that's the formal terminology that we'll use for these 4 cases: negative, non-positive, positive, and non-negative, okay? Now, what we're going to try to do here is find solutions for these inequalities. Now, unlike with an equality, where there's exactly one solution, with inequalities, there's potentially an infinite number of solutions. All right, so let's see how and why that works. If you know, for example, that, let's say the result of solving some equation or other was that x equals 7, then that means x equals 7, and that's it. That's your solution. You're looking at one point on the real number line, and that's it. Right here, that's your solution. But when it says less than or equal to, that means that it includes everything from 7 down to negative infinity. So you can actually say we shade it in here, including the 7 all the way down to negative infinity. So you literally have an infinite number of values in your solution set. So it's a set rather than a single number. And that's a key detail. Yes, exactly. The fact that there's an infinite number of solutions rather than just one. All right. Now, we're going to show how to algebraically manipulate an inequality to come up with our solutions. And we're going to see that, for the most part, it's exactly what we've been doing, but there's one critically important difference. All right. Number one, if let's say we have something like this, A is less than B. Well, then if I add a constant C to both sides of this inequality, I have not changed the results. In other words, if I had, for example, 3 is less than 7, if I added 2 to both sides, I'll still have an inequality, a valid inequality. Nothing's changed. If I subtract 2 from both sides or add -2, I'll still have a valid inequality. All right, so when it comes to addition and subtraction, I can solve for a linear inequality by doing what I would normally do, which is to say I can add a constant to both sides, or I can subtract a constant, and I will have the exact same result. These are still both valid statements. All right, now, having said that, though, things can be very different when it comes to multiplication and division. Okay, so this is what we're going to see. Let me just throw some examples there on the next slide. So A is less than B. If I have A is less than B, and I now multiply both sides by a constant C, this works unless, or let's just say not unless, but if C is positive. Okay, so this is different than what we've seen. This is true only if C is positive. In other words, if I start out with 3 less than 7, and I multiply both sides by 2, I'll be left with this valid statement. But what happens in this case? What if I multiply both sides by -2? Uh-oh, is this now a valid statement? It is not. So what we have to do when we multiply by both sides by a negative number is we have to reverse the direction of the inequality to make it a valid statement. Notice this is true now. But if you notice what I had to do, by multiplying both sides by -2, we must reverse the direction of the inequality because we multiplied.
Erie County Legislature Chairwoman April Baskin, and I'm inviting you to sign up for this year's 2021 Buffalo Black History Week, hosted by myself.
All right, so therefore, we have to remember that multiplying by negative number, now with equalities, this was never an issue, but now it is an issue because these are now negative numbers. And so a -6 is actually larger than -14. So we're changing the direction. Now, if this is true for multiplication, it must also be true for division. All right, so if we had something like this, let's say we started out with 4 is less than 8, and I decided to divide both sides by -2. Well, guess what? This statement is no longer valid, is it? It is not. So once again, we have to reverse the direction of that inequality to make this a valid statement. So again, we must reverse the direction of the inequality because we've divided by negative numbers. So the bottom line is addition and subtraction are unaffected, but multiplying, dividing, we have to be careful with negative numbers. Now, if we're doing this with positive numbers, we don't have to worry about this. It's only with the negatives that this becomes a problem. So you probably knew this at one time. You may have started to forget about it, but yes, with inequalities, when we multiply or divide by a negative number, we have to reverse the direction of the inequality. All right. Now let's do some examples. Now, some of these will be very simple and some of these maybe not so much, but if we start out here, for example, with this case, 2x minus 7 is less than or equal to 9. How do we solve for x? Well, we use the usual techniques that we already know. We add 7 to both sides, which we're allowed to do, even with an inequality. And now we'll divide out by this +2, so we don't have to change the direction. And we're left with x is less than or equal to 8. And you can double check this very easily by saying, well, you know, any number less than or equal to 8 should satisfy this inequality. Let's find out. Let's try, let's say x equals 7. Is it true that 2 times 7 minus 7 is less than or equal to 9? Oh, yes, it is. Okay. And you can put any number from 8 down to negative infinity in there, and you'll get the same result. Okay, it is a valid statement. Okay, now how about this one? This one's trickier because there are negatives involved. So in order to get rid of that -4, I don't want -4x. I need x at some point. So no matter what I do, somewhere along the way, I need to get rid of that negative. In this case, I'm going to start by multiplying both sides by -1 to make it a lot simpler. But again, if you notice, that means I must reverse that direction. And so therefore it's 4x minus 5 is less than or equal to 7. Now we're good because we just have to add 5 to both sides. And we'll have 4x less than or equal to 12. And then we divide out the 3, which certainly is not a problem. And we have x is less than or equal to 3. And for a double check, now we can plug in any number less than or equal to 3. Let's try 0. Is it true that minus 4 times 0 plus 5 is greater than or equal to negative 7? Yes, it is. And we're all set. All right, let's see if we've got another one here that we can work on. Let's try this one. Now, this one is interesting because it turns out that all these numbers happen to have a common factor of 25. If you notice that, that's great. If not, you can just carry on the normal way, but look how nice that makes our work here. X minus 3 greater than or equal to 4. And now I literally just have to add 3 to both sides. And I've got myself x greater than or equal to 7. Very good. Now, what I'd like to do is add a couple more of my own examples that I'm going to make up right now because I think we could use a little more practice. All right, so there's nothing better than practice for this type of thing. It's the only way that this will ever work out is with practice. So let's try this one. How about, let's see, minus 2x minus 8. Oh, all right, try that one and see what you come up with. Oh, somebody's got an answer. All right, whoa. All right, minus 12. All right, let's find out. So add 8 to both sides. Minus 2x less than or equal to 24. Now I'm going to divide out that negative 2. And so that means I have to reverse the sign. So that means I have x greater than or equal to minus 12. Perfect. And again, we can double check. Anything above negative 12 will do. So let's let x equal 0. It'll be so nice and easy. Minus 2x minus 8 less than or equal to 16. Minus 2 times 0 minus 8 less than or equal to 16. Perfect. All right, that was good. All right, one more, and that's it. I think we can go on to the next topic. Let's see, what can we do here? All right, make sure though, if you did get negative 12, that make sure that its x is greater than or equal to negative 12, not less than or equal to. All right, here's another fun one. Oh, somebody got it already. Okay, -1. Okay, let's find out. First thing I'm going to do is multiply both sides by -3. Now, again, this is not the only way to do it, but it's one possibility. So I'm going to have x minus 18. Oops. Okay. Well, let's keep going. I multiply both sides by -3. So I've got positive x minus 18. I reverse the signs. Now I'm going to add the 18 to both sides, of course. So x is greater than or equal to -9. And again, we can double check. We can throw in any number greater than or equal to -9. Let's try 0. And that works. Beautiful. All right. All right, that's it. All right, I think we had enough of that. Now let's move on to a new topic, which is called binomial expressions. Now, a binomial expression has a couple of requirements to be called a binomial expression. First of all, it has to have 2 terms in it. And that should be clear from this bi prefix. But then the exponents, any exponents in this expression must be whole numbers. And you'll recall from the first week of the class that the whole numbers are 0, 1, 2, 3, 4, etc. So that means, though, that let's say you have a constant like 6. Think of 6 as being 6 times x to the 0 power. And so because this is equal to 1, so that means that a binomial expression can include constants. So in other words, it'll have constants and it'll have x's whose exponent is one of these numbers. Anything else means it does not qualify as a binomial expression. All right, now let's see some examples of cases that work as binomial expressions, like these. Now, remember, we said that constants count because they could be thought of as, like, for example, in the first case, this is 2 times x to the 0. This counts too because this x has an implied exponent of 1. All right, so these mean the same thing. And of course, 1 is a whole number. This counts, of course, because 2 is a whole number and we have a constant over here. And then finally here we have a 3, which is fine. The fact that this is a negative coefficient doesn't affect anything. It's only the exponents that have to be whole numbers. Oh, and of course, one more detail here. They all have 2 expressions. If they don't have, two terms. If they don't have 2 terms, then no matter what they are, they do not qualify as a binomial expression. All right, that's got to come first. Once we confirm that they have 2 terms, then we can just check their exponents and we see whether or not they work. Now we're going to look at some cases that do not qualify as binomial expressions. The challenge is to figure out why. All right, that's actually kind of more fun than this. We're going to see cases that do not work, but we have to figure out why. How about this first one? What's the problem? Isn't the exponent of x 1? Why is this no good? What's the problem?
We have a variable in the denominator.
It's in the denominator, right? Because 3 over x equals 3x. Ah, there's your problem. -1 is not a whole number, is it? And that means no. Okay, so in other words, yes, even though it's 1 in the denominator, which means this expression is actually 3x to the minus 1 minus 9. So that means it's no good. This one, for the same reason, you notice how we have -2, which is not a whole number. And therefore, it doesn't qualify as a binomial expression. There's a problem here too, 0.5. Not a whole number. There's that's the problem there. And of course, this is the same thing as 5 radical x minus 7. No good. And then the 4 is fine, but there's only one term here. That rules that one out right away. So all 4 of these would be none of these would be considered to be binomial expressions. All right, so now what we're going to do next is something that you've seen before, but maybe not for a while. It's like an old friend coming to visit. As soon as I show it to you, you'll say, oh, yes, I remember very well. And that would be FOIL. Okay, nobody forgets about FOIL. FOIL, of course, is an acronym, and it stands for first, outer, inner, and last. That worked out well. I mean, it's the fact that it's an easy word to say makes it stick in your memory. And that's where we got lucky here. Acronyms are designed to help us remember words and make them a little simpler. And so this is no exception. FOIL, first, outer, inner, last. So exactly how does that work? All right, let's look at an example of this where we have two binary or binomial expressions, and we're going to use FOIL to multiply them out. Because ultimately the job of FOIL is to take a product of two binomial expressions and convert them into something else. Now, that something else could be almost anything. But in the simplest cases, it usually ends up giving us what's called a quadratic expression. So, all right, let's see an example here. So these are both clearly binomial expressions because we have an implied 1 here, and these are constants. So both are binomial expressions, and the reason why we stress this is because FOIL only works with binomial expressions. So as far as the FOIL goes, this is what we mean by F, or first. O, or outer, is these two. We're multiplying these together. Inner is the product of these two terms. And last is the product of these two terms. All right, first, outer, inner, and last. They're all products. And when we're done, we'll have 4 products that we can add up to come up with our new expression. All right, so let's go to the next slide and see exactly how that works out. Okay. All right, here we go. So again, this is F. X times X, as you can see here, is X squared. O is these two. X times 4. I would be these two. -3 times X. And then finally, last would be these two. -3 times 4. So when you write these out, you can see that 2 of these can be combined. And so that tells me that this product equals X squared. Yeah, go ahead, Noah.
So this is basically a form of the distributive property, right?
It is. That is what we're doing here. We're distributing one over the other. That's correct. And so we end up with X squared plus X minus 12. So these mean the same thing, but this is now what we're going to call a quadratic expression.
What happened with the 4x and 3x?
Oh, we added them together.
Oh, okay. Got it.
Yeah, there's no point in writing them separately. We just consolidated them. That's why that happened. Okay. Okay. So it's called quadratic, by the way, just because there's an x squared term in there. Quadratic means x squared is involved somewhere. Okay. Linear means there's no x squares, there's just x, but quadratic means there's an x squared term in there. All right, so, there we go. What we're gonna do now this is for practice purposes. What I'd like you to do is take this following expression and use FOIL to write out the equivalent quadratic expression, okay? So use your FOIL skills and tell me what this is equal to. Oh, yes. Go ahead.
I remember another method that I used to use in high school, and I don't know if we're gonna cover it here, but it's the box method.
You know, it's interesting. In the other class, they mentioned that as well. And I have to admit, I mean, I had not heard of it before. And the girl in the other class who mentioned it, she sent me a diagram of it, and it didn't look familiar at all. Now, having said that, if you feel more comfortable using the box method, you can feel free to go ahead and use it.
Okay.
Yeah, whatever makes you comfortable, go ahead. If you like the box method better, you should use it. This is essentially the same thing, only organized a little differently.
So on the test, there's not going to be any questions asking to use a specific method, is there?
No, it'll
Okay.
just say, what is this expression equal to, or something like that. If I don't think so. If it does, I'll change it, because I don't want to like force you to use a technique that you're not comfortable with. Whatever gets you to the answer, you know, that in the real world, when you're doing math, you do whatever works. And there's always at least a few techniques. In fact, there's another technique that you can use, which I'm going to show it to you when we're done with this example, because it might ring a bell too. Although I know now that it's not the box method. But you know what I think probably happened? You know, somewhere along the way, somebody decided that, you know, there must be people who do research about math education. And sometime after I finished with school, somebody came up with this method, the box method, which they believed was simpler. And so you learned it and I didn't. And so this is how this happens. I do not know if it's easier or not. That's, I guess, we'll leave that to those education people to decide. But the FOIL, did they at least show you the FOIL method, or is it
Oh
completely?
yes, of course.
Did they tell you that they thought one was better than the other?
No, it was more like, well, here's the FOIL method, and then we learn that, and then, well, here's the box method, and then learn that, and then afterwards it'd be like, apply both. So like, here are some things where you use FOIL, here are some where you use box,
I see.
just to get the practice in.
All right. Okay. So anyway, let's do this one with the FOIL. Then I'll show you yet a third technique that you could try if you want to. But I have a feeling that you've never seen what I'm about to show you. So, but let's finish this one up. So here's the expression. Here's FOIL. Oh, somebody, forgot the negative. See how easy that is? Negatives are the bane of our existence in mathematics, don't you think? It's so easy to mess them up. All right, so we have first 3x times 2x, 6x squared. Outer is minus 10x. Inner would be then minus 9x. And then finally, last would be these two, It's positive 15 because there's two negatives here. Don't forget about that. And then these two can be consolidated. So you'll have 6x squared. Now, if you want to, you can write it out like this first. Then you'll see it pretty quickly that these can be combined, and you'll end up with 9x squared minus 19x plus 15. Now, you know what? I'm just thinking, now that you brought this up, I'm going to go look at the problem set number 6 for a second. I just want to make sure that I didn't actually say the words, you must use FOIL. Ah, okay. Hold on one second. Because I know the box method is very popular. All right, I'll tell you what. You see here where it says use FOIL? I will tell you right now that you can do anything you want here, okay? So it says FOIL, but if you want to use the box method, that's fine, because ultimately all we care about is the answer. All right, so you can take that to mean use whatever technique you need to get this done. All right. Now that we've done all this, let me show you the technique that I learned. And you'll say to yourselves, maybe you'll like it, maybe you won't. Let me show you how another option, and it's possible you've seen this before. So again, we had 2x minus 3. And we had, I'm leaving room so you can see what I'm doing, 3x minus 5. So this is a technique that I was shown these many years. And what this does, the idea here is to do this. You start in the bottom right-hand corner, you're going to oh, no, you don't like this technique? Oh, all right. Well, we're still going to see how it works. I'm not going to tell you to use it or not use it, though. Go up. The product of these two is 15. Then we go across. The product of these two is negative 10x. We go across, negative 9x. We go up, x squared. And you line them up properly, you get 6x squared minus 19x plus 15. Now, I do not know if there's a name for this technique, but the advantage of this technique is it is not restricted to binomial expressions, which FOIL is. And I'm not sure about the box method. I don't know enough about it, but I'm not sure the box method is restricted to binomial expressions or not, but this technique is definitely not. So therefore, it's not a bad idea to maybe get some practice with it, but you don't have to. If you don't like this technique, don't use it. Okay, it's like anything else, you know. Just do whatever it takes to get to the answer. Use the box method, use FOIL. If you don't like this one, that's fine. It will not take offense, okay? But ultimately, they're all doing the same thing. They're just, somebody sat down and dreamed up this visual way of trying to explain what's happening, and this is what they came up with. But because when I was in school, this is what we were taught to do, this method is very comfortable to me. And maybe they've abandoned it since then in favor of the box method. I don't really know. But anyway, why don't we try this one using any technique that you feel like using? How about that? But the slides are set up to show you the FOIL method. All right, so take a minute and be careful with those negatives. I can't really stress that enough. Be careful with those negatives. All right, let's see what we've got. 8x squared minus 20x minus 8. That sounds right. Why, yes, that is correct. All right, and let's see why. So if you're doing FOIL, you get first is here. That's going to give us negative 8x squared. Outer is here, minus 16. Inner would be these two, minus 4x. And then last is negative 8. So you got minus 8x squared. You can write these out separately, but then you'll notice that you must or should combine all the like terms, and you will in fact get negative 8x squared minus 20x minus 8. Yes, so the two people who answered are absolutely correct. Very nice. The three people who got it. That's right. I'm sure you all got it. Now, we're going to introduce, as we started to mention earlier, this very important idea called quadratic equations. Now, the quadratic simply refers to the fact that there's an x squared in there. So imagine that we have an expression, like an example could be, for example, 2x squared plus 4x minus 7. I'm just making that up. So in general, a, b, and c are the coefficients of, a is the coefficient of x squared, b is the coefficient of x, and then c is some constant. Now, the only real restraint here is that a is not going to be 0, because if it is, then we'll just end up with a linear equation. So assuming that these are quadratics, a is never going to be 0. Now, here's the thing. What we're actually seeing here is what's called a, or you actually, maybe you can tell me, this type of graph always looks something like this. Okay, and the key here is that it crosses the axis twice. There's 2 points where, so let's call this x1 comma 0 and x2 comma 0. And we say that x1 and x2 are the solutions of the quadratic equation. So this curve has a special name. Does anyone remember what it is?
I think it's called a parabola.
That's right. It's our old friend, the parabola. All right. Now, here's a fun little twist that you might not have anticipated. It turns out, and I found this kind of by accident, that there's a website which is called Symbolab, where you can actually ask it to graph things like this for you. So let's say I ask it for 2x squared minus 4x plus 10. Okay, Symbolab. Now you notice these are very happy people because they're in a math class. You get the idea here? It's math. Woohoo, it's fun. So therefore, we're going to hit go, and we'll ask for the graph. And wow, look at that baby. Ooh, I did something very bad here by mistake. Let me show you. Hold on one second. Let's try that again. Let me try a different one, because I was just making it up. There we go. I actually picked a case where it did not cross the horizontal axis. Here we go. This is what I was hoping for. Now, if you look at it carefully, it does cross the horizontal axis in 2 different places. In fact, the software will actually show you what those answers are. Now, if you notice here, it says 1 plus radical 11, 0. That 1 plus radical 11 is one of the solutions of this equation. If you plug that in up here, you will get 0. It's not a very nice answer, but it works. And then on this side, we have 1 minus radical 11. And either one of those, when plugged into this equation, will give us a 0, which means that these are the two solutions of the equation, 1 plus radical 11 and 1 minus radical 11. Now, the one I had before was a very bad choice, and I'll tell you why. Because if the curve does not cross the horizontal axis like this, this is bad news because, yeah, it means that the solutions are imaginary numbers. And so we know that in this class, imaginary numbers will never happen, will they? No, we've ruled them out completely. And so you will never get a case like this in this class. That will have to wait for pre-calculus, which you're all signing up for, right? Oh, maybe I should take a poll on that one. I think I know what the answer is. No, I shouldn't say that. I'm sure at least some of you might be interested. But yeah, in pre-calculus, we do deal with imaginary numbers, but just not in this class. So we'll restrict ourselves to cases where the curve actually cuts the horizontal axis in 2 different places, and those are my solutions. Okay. And you never know what this could be for. Like you see this a lot in economics. We see these types of functions that might be used to represent, let's say, profits or costs of production. Okay. So anyway, what we're going to try to do here, though, is find those solutions. How did we get this point? How do we know that it's 1 plus radical 11 and 1 minus radical 11? Well, there's 2 different ways we can get to this. We can use either what's called factoring, or another old friend of yours, the quadratic formula, which I'm going to scroll down there and show it to you, and you're going to say, oh, how could I? No, I didn't forget. It's been my experience, by the way, that there's a handful of equations that nobody ever forgets, and this is one of them. There's something about this equation that just sticks in our memories. Let me show it to you. Remember this? Yes, you do. Minus b plus and minus the square root of b squared minus 4ac all over 2a. That is the quadratic formula. You've all seen it. You've all known it. And it's still stuck there when you need it, isn't it? That's right. It stayed there, and it's still there now that you need it. It's probably been a few years since you were first introduced to it, and yet it's still there when you need it, isn't it? Even when you try to forget, you're not, you know, the thing is about your memory is you can forget by accident, but you can't intentionally forget something. If it's still in your memory, it's still there, and you can't pretend otherwise. You can't unlearn anything, all right? It's almost like you have an enormous closet where you're not allowed to throw anything out. It may get messy in there and hard to find stuff, but everything is still in there. And so all this wonderful knowledge you accumulated throughout your career in high school and below, it's still there. You may not be able to find it quickly, but it is there. And this is one of them. And so now you realize, wait a minute, I still need this. Why don't I dust it off and bring it back so I can use it? All right. So no matter how thick the cobwebs are, it's still in your memory closet, isn't it? Oh, yes, it is, whether you admit it or not. All right. Did anyone here actually forget it? I bet you didn't. Why do you think that is? I don't know. There's just something about the way our memories are organized that this type of information just sticks. A song. Oh, okay. Now, I didn't expect that. It's hard for you to imagine. Imagine a song about the quadratic formula. Do you think that could ever be like a big bestseller, maybe a gold record? The quadratic formula song. Is it classical music? Is it hard rock? How does that go? All right, but anyway, whatever it takes to stick it in your memory, you have to do it. Yes, imagine how cool that would be, an opera about the quadratic formula. I bet it could be done. But anyway, let's get back to this. Before we do our quadratic formula, we're going to go back and do something called, where are we? I lost it. We're going to take an approach called factoring. Now, factoring is basically, in effect, with factoring, you're basically reversing the FOIL process. It's a bit of a challenge. It works well for very simple cases, but eventually it becomes too awkward, and that's when we want to switch basically to the quadratic formula. So what exactly are we doing here? All right, let's look at an example. This is a quadratic equation, and if we go to Symbolab, let me just quickly type this in here. X squared minus 3x minus 4. And I'm going to graph it, and you'll be able to see visually what the solutions are before we even look for them with our factoring technique. So here it is. The solutions will be 4 and -1. Okay, so we already know what the answers are, but now we're going to see how to find them. We can't always assume they'll have Symbolab at our fingertips. Oh, sure, go ahead.
So does it matter that the vertex is not on the y-axis, or is it like as long as it intercepts the y-axis?
It doesn't actually, it has to eventually cross the y-axis.
Okay.
But what we care about is not that, but where does it cross the x-axis? Okay, it might take a while to get to the y-axis, but it will reach it eventually. So what matters for our purposes is just where it crosses the x-axis. All right, so let's see how you would find these solutions with our factoring technique. Now, what I'm about to show you is going to look very bizarre and abstract for a few minutes, but once you get the hang of it, you'll start to say, this isn't bad. All right, so let's start with the bizarre and abstract part. Ooh, that looks very bizarre and abstract because I have letters instead of numbers. So if you took FOIL and applied it to these two expressions, you would come back to this. So we're taking the expression and working it back to these factors. Now, how does this help us? Well, it means that whatever these numbers are, we can identify them because we have two pieces of information. Whatever n and m are, their product is this term, and their sum is this term, and their product is this term. It turns out there's only one way to do this. No matter what numbers we have, there's only one way to do this. So let's look at our first example again. The one we've already seen, the answer is 2. And whoops, let's see how this works for our example. So here, for example, this case, it turns out that the sum of this n and m is here. And the product is here. Okay, now here's how we're going to identify them. If you notice, you remember this rule from somewhere along your travels. We have two equations, two unknowns, and that means we can solve for them. Do you remember that? Does that ring a bell? Two equations, two unknowns? You have to have the same number of equations as unknowns to solve for these variables. Well, here we have, let's start here. Now, we're restricting ourselves here to integers, by the way. So what integers have the product -4? How about 1 and -4? How about -1 and +4? 2 and -2, -2 and 2. So for all of these pairs of numbers, their product is -4. But we also need the pair of numbers to have a sum of -3. So out of all of these, in which case do we have a sum of -3? Oh, here we go. So that implies that x plus 1 times x minus 4 equals x squared minus 3x minus 4. And we can double check that with FOIL or the box method, whatever you like best. Let's do that. Actually, I've already done that. So let's jump down and see how that works. X plus 1 times x minus 4 equals our original function, x squared minus 3x minus 4. Let's prove it with FOIL. Okay, x plus 1, x minus 4. Here's f. Here's O. F is right here. O is here. I, the inner, is x. And then last would be these two, which is -4. So I have x squared. If I combine these two, I get -3x. And this constant is -4. So guess what? We're done with that. But there's one more step. We are interested in the factors, but only because we need them to help us find the solutions. Remember, the whole idea here is we're looking for the points where the function crosses the axis, and on these points, y equals 0. So what we're going to do is set these factors equal to 0, which implies that if either one of these equals 0, the entire expression will equal 0. So guess what we just did? We just proved that these must be our solutions. -1 and 4. Now we saw this on Symbolab, but why don't we do this? Why don't we prove it? And how would you do that? You plug these numbers into the function one at a time, and you try to show that it does in fact equal 0 when we have x equals -1 and when x equals 4. All right, so let's do that. I think it's already here too. I think I've already jumped ahead. Here we go. So let's prove it. So when x equals -1, if you plug it into this formula, or this equation rather, you'll find that you do indeed end up with 0 equals 0. So this one works. Nice. And what about the 4? Does that one work? Let's see, plug it in, and do you get 0 equals 0? Yes, you do. So what this means then is that the factors of this equation are x plus 1 and x minus 4. The solutions, though, are x equals -1 and x equals +4. And that's what all we need to know. So, but the factors really aren't as useful as the solutions. The factors are really just a way of getting to the solutions. That's what we ultimately are after. All right, are we ready for another example? Yes. So in the next example, we'll have a quadratic equation. What I want you to do is find the factors and then use those to find the solutions. All right, and then when we're done, we'll confirm that we can double check it ourselves, and we'll also look at it in Symbolab. All right, so here we go. Let's try this one. All right, take a couple of minutes, find the factors, find the solutions, and then we'll double check it. Oh my God, somebody's already got it. Boy, that was fast. 2 and 4, yes. All right, let's let everyone have a chance to catch up. It is in fact 2 and 4, but let's see why. All right. It's actually, no, it is 2 and 4. Those are the factors. Yeah, so the factors, let's see on the next page here, it shows that if you take, let's do it right here. I need two numbers whose product is 8, and yet whose sum is -6. So let's try some possibilities here. Oh, here we go. So that means that the factors are x minus 2 and x minus 4. So if you apply FOIL to these, you'll see that they do in fact add up to x squared minus 6x plus 8. So that's the starting point. In fact, somewhere down here, I think I've already demonstrated it.
I have a question real quick.
Yes, go ahead.
How did you get 1 and 8? Like how did you get the 1 when
Oh.
you
Oh,
yeah.
these are just possibilities. 1
Oh,
times
okay.
8 is 8. 2 times 4 is 8. -1 times -8 is 8, and so is -2 and -4. So I'm writing out a list.
Oh, I see what you did.
Yes, exactly.
Okay.
Of all the
Thank you.
integers whose product is 8, and then I pick the one whose sum is -6. And there will always be
Gotcha.
room.
Okay.
And those are my factors, which you can prove with the FOIL. But the solutions, though, are obtained by setting these equal to 0. So you split it up and set each one individually equal to 0. And you come up with 2 and 4. And again, you can confirm this by plugging them into this equation. This I have done here. Hold on one second. Let me just find them. Oh, yes. So I did do this with FOIL. First I proved that this is correct. If these are your factors, if I apply FOIL to them, you'll see that I do end up with x squared minus 6x plus 8. So that part is correct. Now the question is whether or not x equals 2 and x equals 4 are the solutions. To do that, to prove that, we need to take them and plug them back into the original equation. So here I've done it with 2. Plug it into the original equation, and it does in fact give us back 0. So we know that one's good. And then we're going to try 4, and voila, it is in fact 0 equals 0. So the solutions are indeed x equals 2 and x equals 4, which means you end up with something like this. They're both positive, so it's contained on the, oh, I didn't draw this very well. Let's try that again. The key is that where they cross on the horizontal axis, they're both positive. And of course, we can use our new friend Symbolab to prove this. Let's try it. All right. And when we look at the graph, you should see it crossing the axis. Yeah, here it is, 4, 0, and 2, 0. So it confirms what we knew already, that those are the two solutions. All right, now the moment you've been waiting for has arrived. We're going to get our hands on that old quadratic formula that we know and love so well. What we're basically going to do is confirm these results one more time. We're going to find the solutions to these two equations using the quadratic formula. All right, so remember the original one was y equals x squared minus 3x minus 4. And we've already seen that its solutions are 4 and negative 1. We're going to prove it now with a quadratic formula. Now, this is based on the logic, by the way. Don't forget, these letters are coming from this expression for the quadratic formula. So b is the coefficient of x, a is the coefficient of x squared, and c is the constant. And the plus and minus means that there's two solutions. All right, so why don't we plug these in for our first, remember we've already done this one, but let's try it now with the quadratic formula. And so here's what I'm going to do. I'm going to move these to a new slide. You can follow along with the logic. I'm going to copy the equation back here. And remembering that in this case, a equals 1, b is negative 3, and c is negative 4, because the original equation was x squared minus 3x minus 4 equals 0. So you're going to do some plugging in. And what I'd like to point out to you is that you've got to be extra careful with all those negatives. So here I'm giving it to you basically. I just want you to follow through the logic, or else you can write it down on your own piece of paper and confirm that you can do it. But this is what you're actually doing. All right, I want you to take a look at this and see. And at the end here, by the way, again, this plus and minus, if you reduce all of this, at the end you have 3 plus and minus 5 halves, which means you're rewriting this as 3 minus 5 over 2 and 3 plus 5 over 2. And that will in fact give us what we were looking for, the solutions of negative 1 and positive 4. And if you notice, we did get lucky here we have a perfect square under the square root sign. And I do want to point out here too that this expression, if you get a negative under the square root sign, that means you've done something wrong, because we're making sure that that never happens in this class. That would give you an imaginary solution. So if you do have a negative here, that means you should check what you've done, because you've got a mistake. All right, beautiful. And in fact, so you can see that as an alternative to factoring, we're able to use, you can always use the quadratic formula and you'll end up with the right results. Sometimes factoring could be a little quicker, but only for cases where this equation isn't all that complicated. In particular, I would never factor unless the coefficient here is 1. After that, it starts to get really, really messy. All right, so just to prove that you can, let's show off our ability to use this formula. Let's go to our second equation, which we've already seen a few minutes ago, and apply it to the quadratic equation, remembering that we already have determined that our solutions are 2 and 4. So what I basically want you to do is confirm that with the quadratic formula. All right, let's see how we did. So again, plug everything in carefully. All right, in this case, A, we had x squared minus 6x plus 8. A is 1, B is -6, and C is 8. All right, so again, you just have to be super careful with all these negatives. But as you work your way through, you'll see that, oh, good news, we have a perfect square. So we have 6 plus or minus 2 over 2, which is the same thing as saying 6 minus 2 over 2 and 6 plus 2 over 2, and those reduce to 2 and 4. Beautiful. This is one of the reasons why it's our favorite formula of all time, I think. It works so nicely. All right, you just have to watch out for those pesky negatives. All right, now here's an interesting example of how to use this in practice. You might not think so, but this is actually going to be an example of the quadratic equation. Let's look at this thing. It'll be fun. We have a carpenter building a table. Oh my God, it's a rectangular picnic table. Now, if you recall, with a rectangle like this, we have a length and a width. And the area is simply, very simply, the length times the width. Now, they're telling us the length must be 2 feet more than the width, and the area must be 35 square feet. So why don't we do this? Let's let x be the width, and the length could be x plus 2. That satisfies our requirement that the length is 2 more than the width, although you could have had x and x minus 2 just as easily. And now the area is the length times the width. So you'll have x plus 2 times x, and that has to equal 35, which if you rearrange it slightly, oh my God, it's a quadratic equation. And so you can solve this equation to discover the correct value of x, which is the width, and then of course the length would just be 2 more than that. So again, here's a golden opportunity for you to practice by applying the quadratic formula to this quadratic equation. And let me know what you get for x. All right, so there's some people in this class who are super fast with this. So let's see what you get. All right, some helpful hints. A is 1, B is 2, C is negative 35. Here we go. All right, now it actually is 5 and negative 7. So if you have 7, double check your numbers. 5 and, yes, it's negative 7. Now you probably are asking yourself, wait a minute. What's going on here? This is fine. This is correct, but guess what? Can the length or can the width be negative 7 feet? It cannot. So that means we can only use the solution x equals 5. So therefore, when you go back to our original diagram, you'll see that the width is 5, the length is 7. Does that satisfy the requirement that the length is 2 feet greater than the width? Yes. And is the area 35 square feet? Why, yes, it is. So who knew? So imagine your carpenter is also a good mathematician, and he says, you know, you told me what I have to do. I use the quadratic formula to determine that the table has to be 7 feet by 5 feet. You'd be pretty impressed with his math skills, wouldn't you? And you should be, because that was pretty clever, I must say. But you can see that in the real world, you do run into these scenarios. Like, for example, if your result is in dollars, dollars can't be negative either. So that means you have to use the positive solution. Okay, and this does happen sometimes. So anyway, now having said all that, I did mention before there is a chapter 6 problem set on Moodle, which I would like you to look at between now and Thursday, so we can go over it together and make sure that we're catching on. Now, when that's done, it turns out that the first midterm is based on chapters 5 and 6. So, but before we do any midterms, we're going to go over what's called the sample midterm, which is a jumble of all the questions from 5 and 6, so we can make sure we really understand everything. And when that's done, then you can have your midterm. Now, somebody else in the other class was worried that it's going to be as long as these problem sets. No, it was meant to be given out in a class in person that lasts about an hour and 40 minutes. So it can't be as long as those problem sets. It was meant to be done in the classroom in under an hour and 40 minutes. So it's kind of like, think of it as sort of a random sampling from all the problem sets that we've been doing. So we'll discuss that later, but for now, why don't we focus on doing the chapter 6 problem set between now and Thursday, and we'll just make sure you're really following along and understanding everything. Okay? And then I will give you the sample midterm to work on, and then we can take care of that, and then I can give you the midterm. And in the meantime, we can dive into something completely new. All right, something very new and exciting. It involves money. Okay, so anyway, if there's no last minute questions, we'll stop it right here. And I'll see you on Thursday with your answers ready from the chapter 6 problem set. Okay. All right, so see you then. Okay, see you later. All right, I can stop the sharing now, but we'll still be in the meeting.
Yeah, okay. So a few weeks ago, I think I sent you the pass fail form.
Oh, all right, I'll get it. I just forgot. I'll take care of it today.
Okay, do you know if it's like already supposed to be in?
I don't know. If I tell them to let you do it, they'll probably let it go. I don't remember. I've never had this request before. I thought, I wasn't even sure if you're allowed to have pass fails.
I think you are.
Okay. I'll ask them and see what they say. You're sure you want to pass fail? You don't want to get an A or a B?
I'm not gonna get an A or a B. This is math.
Okay. All right. All right. I'll ask them and see what they say.
Thank you.
Okay. All right. Bye.